Now you can.
That's it. Now it's working. Yeah, sure. So, all right, let me just get to the right place. There we go. So, okay, I'm going to be talking about X-ray CT for additive manufacturing in particular. It's a kind of an overview presentation of many applications and uses of CT for additive, but also some latest trends in AI, which I hope to get to. That's why I'm going to try and cover some slides quite fast. So just background, the introduction already explained. I'm a research professor at Stellenbosch University until 2021, but where I'm still affiliated, but I'm now working with Object Research Systems, which makes the Dragonfly software, so a software company. My research interests are in additive manufacturing, of course, and also X-ray tomography applications and characterizing new materials, and also biomimicry, so learning from natural structures for engineering applications. So those are my links. If you want to get in touch, it would be very nice to connect and keep in touch like that. So this is the book that was mentioned. It's a book I was honored to take part in as an editor, and it's covering all basics about laser powder bed fusion, also known as selective laser melting. It's one of the most popular industrial additive manufacturing methods for metal parts. So I will talk a little bit about why X-ray CT, especially why for additive, and then moving to typical applications, and then some examples, so specific examples of some of my previous work to explain how CT is useful in this field. And then finally, artificial intelligence and how that allows automation of this kind of work and the benefits of that. So first of all, why CT? It's non-destructive, so it allows you to look inside objects and make cross-sections non-destructively, so that you don't have to lose a part and lose money because of that. You get a real inside view without cutting them open. It's in additive specifically useful for detecting flaws, so looking for porosities or cracks or inclusions. Also quantifying those flaws, so determining what the size is of them and where they are in 3D is also for additive manufacturing quite important because of the manufacture method and the mechanisms involved, and sometimes cause localization of pores, and it's important to know about that. CT also allows dimensional measurements, so you can measure internal features, hard to reach features, and measure wall thicknesses across a part in 3 dimensions, which would have been very difficult otherwise. Well, it's also possible to make an evaluation about how a part compares to its intended design. So you can align these two design and actual part data sets together and see how they deviate and quantify that and determine if that's sufficient for the application. So there are still more. This slide is about more like the newer applications. It's also useful for powder characterization. So powders are often feedstocks for many AM processes, and characterizing that powder can be very useful. Also, it's possible to evaluate surfaces, surface roughness, or local surface topography. And actually, additive manufactured surfaces are well suited to CT imaging because they are much rougher than machined surfaces. And CT allows you to see undercuts and features which would have been missed by surface methods, typical surface analysis methods. Then multi-scale CT, that's what that means, is looking at different scales. So a lot like a microscope, you can zoom into very small details, but then your field of view is quite small. So getting an overview of a part and then zooming into certain areas that are critical can be done both, and doing that allows unique insights into your material. So CT can be used in different ways. And then coupons for process optimization. I will show examples of that. So you can really optimize additive processes using CT in a better way than cutting samples. There's also something called witness specimens, which are often built in metal additive manufacturing alongside complex parts like a cylinder or a tensile rod, which is built vertically next to the complex part as a witness of the build process to make quality control and ensure quality control for each build. These samples are meant for destructive testing, but they can actually be CT scanned before destructive tests, which gives you even more information. There's also the possibility of correlating in-process monitoring cameras in the additive build process with post-process CT to correlate process monitoring signals with actual defects, which are seen in CT images. It's also possible to evaluate post-processing, such as HIP processing. Hipping is a process which is used often high temperature and high pressure at the same time to improve the microstructure of additive metals, also to close porosities. And this closing of porosities can specifically be seen quite well by CT. Also, checking lattices and channels for trapped powders is very important in practice, because you have this complexity of design, so you can make internal cooling channels and lattice structures and fancy designs, but if there are powders trapped, that can be a problem for the application, and CT is a great way to check for those kind of issues. You can also create STL files for reverse engineering purposes, and creating a digital record or a digital twin of the data of the part is something of interest for future engineering, for large engineering companies. So there are many more applications. So CT is very useful for many topics in additive manufacturing, but it's not magic. It seems like magic. It's very diverse, but as with all instruments, there are limits. There are some things which don't work, and there are some best practices or best ways to use that kind of tool. And that's sort of what some of my work has focused on so far. Basically, as you know, CT is a way of cutting samples into slices. So there you see an apple cut into slices. That's basically what CT does. That's where the name comes from. Tomos is an ancient Greek for sectioning or slicing. And this is a schematic image of an X-ray source on the left, a detector on the right, and assume, let's just imagine for a minute the X-ray source is like a light beam, a cone beam of light. You would have a shadow for this kind of sample looking like that gray area. And as you turn the sample, you would have different shadow pictures. And by reconstructing into a 3D volumetric data set all those shadow images, or also called projections, you get a reconstructed image where if you make a cross-section horizontally in the location of the red dotted line, you would see quite clearly that there are two objects, even though the shadows don't seem like that in all angles. So that's one way to just explain the process. I'm not going to go into more detail. Basically, the point is a 2D X-ray shadow or projection image looks something like that on a flat panel detector. You don't see a lot of detail in it, but if you build up a 3D volume and you cross-section that part, you see a lot of detail inside that part. And I think I have 2 slides going into that in more detail. Yes, this is a test part which was built in titanium. And what this is there's actually, these are the projection images, the 2D X-ray images. 2D X-ray inspection is used quite often for a quick quality monitor, quality evaluation. It's quite popular in industry. But as you see, even looking at different angles, you don't see defects very easily. You do see there are 2 kind of channel-like features, and you can see this one is quite clearly an open channel, which is straight because you're looking through it at this point. But at the top one here, it's not really clear what that is. It's quite hard to evaluate what that is. If we take the thousands of such images and make a CT reconstruction and then a cross-section through that, you see a lot more detail. And if you make a cross-section in that red plain region there, you see There's some dense metal. The brighter parts are the dense parts, and then the lower density gray is unmelted powder inside this. It's a lattice channel, so it's a lattice structure. It's a channel with lattice structure, and powders got stuck inside. So that's just an example to show the much more detail you get from CT than from 2D inspection. Of course, this is not new. CT is used in industrial inspection, for example, parts like that, looking at specific dimensional measurements, porosity analysis, wall thickness analysis. And I think there's a video here to show that. So typical industrial inspection is for automotive parts, such as this one, where an evaluation is made of the local surface thickness, and then inside the porosities, which these are typical casting pores, which are up to 1 millimeter long, the red one, which is quite typical. And there must be some kind of quality control situation to say that if some pores are bigger than 2 millimeters, then the part is not good. Something needs to be improved in the process and the part scrapped, or parts of that batch scrapped. So a typical CT scan of a cube, this is a 3D printed cube. Let me just see if I can get that video running. So what you see is slices from top to bottom through a 10 millimeter wide cube. And what you see is black dots inside that part. And these black dots are porosities, and the white dots are inclusions. So you see a lot of pores inside, and it's that we're going to analyze here. I will show you a little bit of detail. If you focus in on the biggest pore, you can in that cube, you can see that's where it's located as an example inside. And if you look at it carefully, it's basically very irregular shaped, and that gives us information on the type of pore. It's a lack of fusion pore, which is typically in additive manufacturing due to lack of fusion, which is meaning not enough laser power or too high scan speed, which makes irregular shaped pores in the volume. So porosity analysis is all based on the image pixels. That's why I actually showed this image here with the pixels seen. Usually the pixels are interpolated to look better, but in reality, it's all based on pixels, and then drawing a line between the dark and bright pixels, which obviously with noise is not always a simple task. And that's why there are different ways and algorithms to do it. So it's not as simple as just scanning a part and getting an answer. It's all based on what you do with those images and what you do with it with software. So making a line profile across that same pore, you see a lot of noise, and you have to choose some threshold in order to determine, okay, for example, below that red line, everything below the red line is actually pore space. And if you do that properly across the volume, you can make a really good analysis. You can analyze the pores across the volume for sphericity or for their diameters and so on. And this gives you information on the pores inside, which are typically in additive manufacturing two types. The one is lack of fusion, which you have just seen, and the other is a keyhole pore type, which is more rounded in shape and exists due to vapor cavity in the melt pool, which collapses, which makes large rounded pores, depending on the processing parameters. So the example I showed you, there are many more of these examples that I have produced in the past to exactly create intentionally these different kind of pores by changing the process parameters. So you can reduce the power on the laser while keeping all other parameters constant to create lack of fusion. And then there's one highlighted pore of that in that cube. And in this cube, keyhole pore, which is more rounded in shape. And by changing that over a wide range, you can actually quantify that and see that the porosity varies from 5% down to, in the lowest points here, below almost 0.005% in the volume, which is really, really low values. So it is possible to optimize additive manufacturing, but CT is specifically useful for that because you get the porosity all over, and it's a very, you can quantify really small pores, as in this case, for 5mm cubes, you have a 5 micron voxel size. So pores of 15 microns and up are all quantified. Basically, you can use it for checking a process also, not just optimizing and finding the lowest porosity. These are two different examples. This is a side view of a cube where the build direction is upwards. That means the first bit of this 10mm cube, it's about 3mm, I would say. There's much less porosity in that region than in the top part. So something changed in that process, and that's useful to know about. And in this case, looking at from the top, you see a lot of pores around the contours. So these contour pores are something that occurs quite a lot, and knowing about how much that occurs is important, because pores near the surface can, when there's loading taking place, when there's high stresses, cracks can propagate from the surface to the pore, and that can be the start of further failure. So these are now some further examples. This is an example of lack of fusion porosity in a small cube, but also the same process also in a witness specimen and also in a complex bracket. So often people talk about, oh, but cubes are not representative, but actually that is not correct. If you have some process parameter setting which creates porosities in a cube, those definitely do translate to larger parts. The issue is with unexpected pores which might occur in a complex part. Yes. Hello. Was that a question? Okay. Guess not. So I'm going to move a bit faster here. Basically, these are examples of lack of fusion pores from a small 10mm cube up to a larger bracket of 60mm in length, 40mm in height. Just showing that specific types of defects like contour pores in this case also exist in the more complex and larger parts, not only in these small cubes. Again, proving that the cube is actually useful for optimizing and understanding the process. So there you see pores around the edges, and here you see pores also around the contours, mostly around vertical contours. This is an interesting one where porosities are all just at the top surface of this cube. It's actually an example that we used in a large round robin test, and it's also visible in the cylinder, but only at the top surface. And in the bracket, it's also only on top horizontal surfaces. So it's not all over, but it is also present there. So these are like porosity signatures, and these signatures are present in the witness specimen also. So a witness specimen, as I mentioned earlier, can be very useful for making high resolution CT scan, because this cylinder, you can zoom in on it and make a almost as high resolution scan as on a 10mm coupon cube, while being representative of the actual build across its entire height, because you can scan it in different sections. So now some real examples. This is a student project where some components were manufactured in steel using laser powder bed fusion. There were scans done on the whole part and also on the small cut off parts. And I'm not going to go into too much detail here, just to show that not all scans are the same. If you look at scan number 1 here, the same part scanned 4 times with different parameters, you see quite dark walls in this area. The challenge is that the steel is very dense and it's absorbing the X-rays very, very strongly, which makes the CT imaging quite challenging. It creates some artifacts which make the segmentation difficult. Basically, by optimizing the scan parameters, you can get slightly better brightness across all walls so that you don't have 2 dark walls there. And the one on the bottom right here, scan 4, is sufficient to make an analysis. With such a good data set, you can make some analysis of the deviations from design and highlight where these largest deviations occur exactly. As in this case here, quite clearly, there are some deviations here on the tips, which are important to know about. And overall, it's mostly green, which means it's basically zero deviation. There are also sometimes unexpected things which happen. This is a larger part with some pitting corrosion effect on the surface, which can be visibly inspected even. In order to scan such a part, it's quite a big part. It can be scanned in different ways. It can be scanned at 45-degree loading, like shown on the left, where you then get a full part scan. Or if you're interested in the circled blue region on the right, you can move it up as close as possible to the X-ray source to get a bigger magnification, and then rotate the cylinder or object so that this area stays in the imaging field of view of the scan. And when you do that, you can evaluate, and you can see, as you've seen on the photograph, there are some surface pits, but they don't extend very deeply. And in the corners on this part, you see some unmelted powders with some pores inside, but that is not a problem for this application. Powder characterization. This is just a nice example of a small scan of powders. This is about 2 millimeters across the entire image here, where the powders are typical AM powders, and you have some of them with pores inside, and some of them have actually inside the pore have smaller powders, like we call it a powder filled pore, which is quite interesting and influences the powder flowability. This is an example of roughness, where the white line is the definition of the gradient, the midpoint between the material and air. And as you see there, there's an overhang that is visible, and also some surface penetration or notch-like depressions, which are important to understand. So this, I've used this before to study different process conditions and making test samples with different overhangs relative to the build direction. The roughest surface is the one with the most red and blue, and this is the one that's overhanging the most, basically. So it's not only important to quantify defects, but also to understand which ones are important. And this can be also usefully investigated by tomography because it's non-destructive. So you can make mechanical test samples, scan them before and after some mechanical testing, for example, fatigue testing, where the crack in this case has been already started. So there was a scan done before and then after fatigue testing, and the location of the crack can tell us something about which defect on the surface or inside is the most critical. So I'm going to skip that video there, just in the interest of time. I mentioned about hot isostatic pressing to close pores. As you see there, the left is the sample with pores, and on the right is after hipping, the same exact sample. So it's a very good solution. It closes all pores on the inside. Actually, there are only a few remain which are just connected to the surface or very close to the surface. One example from that work where CT was very useful was, if you look at the sample, there is a pore right under surface on the left, the exact same sample after hipping. That little bit of metal was pierced open by the high pressure gas. So that was quite interesting. These are some examples of lattice structures. Obviously, such kind of structures would benefit from CT imaging. And these are some smaller coupons of lattices which are useful for compression testing. Okay, so now I'm coming to the more latest trends, and this is with AI or deep learning in particular, where porosity segmentation is, as I explained in the beginning, it's quite a challenge and different algorithms could be used. Deep learning is actually quite useful for that, and that's what I will explain here. The idea is that you train a model on 3 slices, like the yellow slices there, and the model does the rest for the rest of the cube to give you a result like that. And what I will show here is with a pre-trained model, which was already trained on a number of images, you can get a decent result. But of course, each sample is different, and the pre-trained model was trained on a number of cubes of titanium and aluminium, and you might have a bracket of a different geometry. In that case, it's identifying some pores, but not all of them. So using transfer learning, you would take the existing deep learning model and then train it to identify these pores. And this is a video of such a training process where 1 or 2 slices have been segmented manually, and then the training takes place over 30 minutes. This is a video which is a little bit faster than real time. But you see that it does find the pores quite successfully there. So it's a nice way to demonstrate that process, and that process is quite easy for the user to do. So this is the result of the transfer learn process, and then you can segment all the pores in the bracket successfully. So I just skipped over quite a few things, but basically there are many ways to use CT, and there are many different machines that can be used for CT or for X-ray tomography or X-ray microscopy. And it depends. It's very difficult to say this is the standardized way to do something because of this wide variety of uses and machines. There are some standards available for using computed tomography as a method, an ASTM standard. There's also a standard guide for metal additive manufacturing inspection using it's a general NDT guide, but has a lot in CT. And there are often research publications. It's important to report in publications the voltage and current and beam filter, of course, also the type of machine, the voxel size specifically that is used, and the reconstruction parameters that are used, and hopefully the image analysis procedure that you use. So which algorithm you use and which thresholding method you use is important to report. Basically to make it reproducible for others. That's the important part. And also for yourself in future. So in conclusion, CT is not only for AM quality inspection, even though it's very useful for that, it's useful for defect detection and dimensional measurement, but it's also useful for giving information about process optimization and understanding your process. It's also good for checking post-processing procedures, like I've shown with the hip example, and especially useful for critical applications and complex geometries where powders can be stuck inside channels or inside lattice structures. And with the complex geometries in AM, these are difficult to evaluate by other methods. So CT is very useful for that. It's also useful for design in terms of looking at bio-inspiration examples, looking at natural structures. I didn't show an example of that, but lattice structures are a porous, repetitive design approach, which is also found in nature. There are many porous structures in nature, and these can be replicated. So there are also some new developments in automated deep learning image analysis using regular software tools without a deep understanding of AI methods. So almost like ChatGPT is becoming mainstream, AI and deep learning image analysis is now becoming mainstream also. And specifically its usefulness is the automation capability. Because it does the work automatically, it can be implemented as part of a macro. So that's particularly useful. So there are some guidelines available, but the main message is there are many ways to use CT, and to make the most of the technology for your application, you need to optimize the workflow to your particular case. And keep in mind, not all scans are equal. And when scans, it's often possible to do more than what you originally think is possible. So yeah, with that, thanks a lot for this opportunity here. I hope that was interesting. And I'm open to questions.
Yeah. Thank you, Dr. Anton, for a very nice talk. We have a few questions in the chat box. So one question is that, are there any material restrictions for CT when other characterization techniques prefer over CT?
Yeah, it's a good question. restrictions, they are not hard restrictions. It's the main challenge is CT works on X-ray imaging. So it works on X-rays have to penetrate the object and you have to get an image of, you have to get X-rays through the object. So very, very large, dense steels, for example, are very hard to image. Like the example I showed of the part with different scans that were needed. Progressively, more and more artifacts take place, which make it very difficult. So I would say there's not a hard restriction, but depending on the equipment you've got, if you want to analyze very, very dense steels of large size, you need a very high X-ray voltage, which is not typical for a desktop CT kind of instrument, for example. So it depends. If you like, there's no restriction. If you have a synchrotron X-ray beam and unlimited time, anything can be scanned. But lab CT instruments typically have some restrictions, and these restrictions are in terms of X-ray penetration mostly, but also physical size, what can be handled in that machine with the rotation hardware and the size of the field of view of the detector and the space available. And also, I guess, yeah, I think that basically covers it.
Yeah, so this question was from Rahul.
When the parts are very big, it's not so well suited to lab CT. So bigger than 300 millimeters is typical, not used in lab CT.
Okay. So yeah, next question is from Harshvardhan. Are there any object geometry restriction for CT? I don't think.
I guess he's talking about because we work in a lab CT with cone beam geometry, and the closer you put the object to the source, the larger the magnification. So the field of view gets smaller. So there's no geometry restriction. It's just that whatever the geometry is needs to fit into the field of view as it's rotating around its axis. So if you have if you want to scan a tennis racket, it would be better to put the tennis racket vertical than to put it horizontal, because then it would more easily fit as it's rotating along its long axis. So it's all about fitting into the field of view of the scan and staying close to the rotation axis if possible.
Okay.
But I think the answer is any geometry can be scanned, and people are often surprised when they use CT for the first time that the quality and the results coming from any geometry is basically the same.
Okay. Yeah, so one question I have that whether this Dragonfly software or any other software play a very important role in resolution, or it is only dependent on the X-ray source we are using. So
okay, I want to answer two things there. The first is the software side of analyzing the images is for me the most important part, because
yes,
with images alone you can do nothing. You can just see inside your part, but nothing can be measured. You really need, the software plays a critical role to extract value from the data. To answer your question about the resolution, the physical voxel size is limited by the magnification of the hardware and the way that you scan the object. So that part has nothing to do with the software. That part has to do with the reconstruction parameters and the magnification of the system. So the resolution itself is not limited or affected by the software. We can, of course, in software modify the data, and you can also downsample the data to make it smaller, make it easier to send to people, or to make it smaller data size. But that's not really what you ask, I think.
Okay. Okay, so we'll take just two questions and then we'll end up. So the question from Kaushik is, can CT data be used, create a 3D model so that we can use it for simulation, like 3D EBST is being used nowadays for grain orientation information. I think they're asking
Yes,
like we can create the 3D model and we can use it for simulation
yes.
purposes.
Yes, you can do that. There are a lot of researchers doing that, and I was part of a team that wrote a review paper on that topic, which was published January this year in I forget the journal's name. I think it's yeah, I don't remember the journal's name right now, but you can search for image-based simulation and you will find that paper. Basically, you take CT data and you create a segmentation of the material, the object, and you create a volumetric mesh of that object and extract that to some simulation software like ANSYS or Abacus and those kind of softwares. So yes, CT data can give you a realistic model which you can use for simulation, for mechanical simulation or fluid flow simulation, those kind of things.
Okay, we'll take one last question. That is from Sasank. Which kind of learning approach adopted by material scientists for image processing through machine learning for CT data? Is a company like ORS Dragonfly going for some software version in this direction?
Okay, so image analysis by AI, there are different options and different software tools available, and some people code their own. Dragonfly uses neural networks, UNet typically, but you can use many different architectures. And I'm not an expert in that topic, but Dragonfly uses neural networks with 2.5 or 3D architectures, which are typical used by all image processing applications. Basically, these are segmentation models, and also you can also create image-to-image models for denoising or for making super resolution or super contrast. So improving your images can also be done by deep learning. But the quick answer is we use typical neural network approaches, and it's quite well advanced already by this time. It's not still experimental. It's quite easy to use and very well developed already.
Okay. Okay. Thank you. I hope the participants are satisfied with the answers. If you have any further question, I request Dr. Anton to please type your email ID in the chat box, or they can get directly on the internet.
Yeah, sure.
So audience, you can directly reach back to Dr. Anton for further questions. Thank you so much, Dr. Anton, for
Thank you very much.
arranging time. I understand your busy schedule.
Thank you very much. Bye-bye.
Like it's a great addition for this event. So thank you so much again.
Bye-bye.
Yeah.
Have a nice
day. Yeah, bye. Take care. So we have our next speaker, Dr. Ziyong Kao. So he has already joined. Hi, welcome, Dr. Ziyong Kao.
Hello.
Yeah. So I'll just briefly introduce about this thing, about the today's next talk. So Dr. Xingyang Kao is currently holds the position of Business Development Manager at Object Research System. So prior to this, he gained valuable experience as a researcher at the University of Saarbrücken, where he focused on the development of pinhole collimators to enable SPECT imaging with the lab PT scanner. He also served as a postdoctoral fellow at Thomas Jefferson University and the University of Pennsylvania. Dr. Kao obtained his PhD in biomedical engineering from the University of Florida. Throughout his research career, he has dedicated himself to investigating the engineering applications of micro-CT. I think I'm pronouncing your name rightly, Professor Dr. Ziyong. So over to you. You can share your thoughts with the audience.
Hello, everyone. It's a great pleasure to be here. And in fact, I would like to have a short demo of Dragonfly. My colleague Anton had a nice presentation about the CT, that X-ray tomography, and then their applications. So for me, I'm going to show you Dragonfly software and with a couple of examples. So you see here, I have loaded the image. This image is a CT scan of the BGA board. So you see this is original reconstructed volume. And we have some process to make it, for example, to make the orientation to be straight with the axis. So I skipped that step. I only show you what I got from the original one. So this is the new one. It was also cropped for a smaller size. So there's some small steps. I just skip them for to save some time. So for this one, we start doing image segmentation, and I'm going to show you the deep learning method, how to segment, most importantly in this case, the pores in the solder balls. Starting with this image, if we do the very traditional way, which is the threshold, the intensity, the intensity threshold, we will probably find the pores have lower intensity than the balls, but it's difficult to differentiate the pores from the background, especially from the other pores, like in this component, which has the exactly the same intensity. But this is not the target that we want segment or we want to label. So the traditional method is difficult. It's possible, but you need a lot of steps, like to crop this specific area, then you remove the background by a few operations. But what I'm showing you now is to do automatic segmentation by AI, especially deep learning method. The result will be like this. Okay, remember, this is the result I get from the deep learning model, deep learning segmentation. And I show you very quickly how to make this happen. You see now I get the result, the labeling result in the pore in the solder balls. In the solder balls, they have been labeled differently than the pores in the other components, like here. And also the solder balls has been labeled differently from the other component, even if they have very similar intensity, like this part and the solder balls. They have very similar intensity, but they have been labeled differently. And that's the objective we want. After this segmentation, we will be able to do a quantification. For example, we're able to see how many solder balls here, and for each ball, how big the pore inside. It could be zero. The porosity is the volume of the pore divided by the volume of the ball, the solder ball. So it could be zero, it could be 10% or 20% or even higher. So this is the typical quantification we do with these images. We start with the image. In Dragonfly, we have a tool called Segmentation Wizard. This is the tool to use the artificial intelligence, especially deep learning, for segmentation. I did this already, so I just show you what I got. It will take typically half an hour to maybe 2 hours, because it's iterative work. You have to label some data for training. You have to train your model. You have to retrain your model with either more training data or another network. So I just show you what I have achieved by at the end. So now I could reopen this object. Then we'll see all the work I have done. So when you first enter this wizard, we call it segmentation wizard, when you enter this first time, you don't have any frames here. Frames means the area we want to use for training the network. And you in the center part, you see that the upper part is the image. The lower part, initially you don't have any lower part. The lower part are the predictions from the model I have trained. In this session, I already have trained 3 neural network, 3 deep learning models. So we have 3 prediction from different model. So we could compare them, see which model predicts better result. The prediction is not saved in the session, so I need to like to predict again. So let me just choose one frame, and all these frames are created. They were created for um, uh, to be used as a training data for training my neural network. And you see, I have 3 networks here. Of course, we don't create too many frames in the beginning. So the first frame, the workflow is like this. I choose an area, I add a frame, then I label all the pixels in this frame. And to label them separately, I need to make a decision in the beginning how many like air regions, how many faces I want differentiate. Like for in this case, it will be the pore inside the balls, and the purple one is the solder balls, and everything else is the background. So in this case, I want to segment them to 3 regions. So this is the first frame I created, and this is second frame. They were placed in different regions because they have different image intensity. They have different image features. So ideally, I need to put frames or place frames to all the representative area of this image, of this data. You see here, I have one to represent the lower part. So by adding this frame, I'm telling the model everything here is not my target, is the background. Even they have the similar intensity as the soda balls here, everything here is to be labeled as the background, which is my objective or my ground truth here. So the model will learn from my labeling, from my ground truth, and how many frames we need for the training data, it depends. So we normally we add a few frames, then we train the model, then we see the prediction, then we add new frames if there's some region is not being predicted well, so we need to add more regions to let the model be retrained with new training data. And sometimes we're not sure what neural network is the best one for this task. So we may train multiple models and to compare them. And though all these 3 models were created and trained, and when you train, you can see how it goes. It was also shown in Dr. Anton's presentation. So you see, this is the history. So I'm replay what I did. So you see for the first round of training, I get my model improved after like 12, 14 epochs. So when I have more epochs, this is the loss function. So loss function is the difference between the ground truth and the model prediction. So ideally, the lower loss function when it's getting closer to 0 means the prediction is very close to the ground truth, and that's what it shows here. I trained multiple times on multiple rounds because I found the model the model predict well in some regions, but it didn't predict well in other regions. So I add more frames later and I trained many times. And this is for example, here. So I trained a second round and the model has been improved. It doesn't predict run in this region. And also I keep adding new frames.
Your voice is not coming. Yeah, it is. Yeah, now it's audible.
Oh, my voice was not good. Now it's all right.
It's okay. Now it's coming. Yeah, please
Okay,
continue.
good. Okay, so you see I have 3 deep learning models here. The difference between them, like the first one, the depth level is 5, and the second one, the depth level is 6. So they are both UNet. Actually, it's advanced version of UNet. And for all this, you can find the reference in our website or the user manual, and it's a standard architecture of neural network. If you search a UNet or attention UNet, I'm sure you will find a lot of references. And we as the software developer, we didn't invent our own neural network. We implemented multiple architectures of the very often used neural network, and UNet is one of them. Attention UNet is kind of enhanced version of UNet, so it's one of my favorite models. When they have a deeper architecture, deep network, it has more parameters, the weights to train. So basically, you need more training data. You need more frames to train a deeper model. Ideally, it will give you better result. And this is something I tried with this data. So if I compare these two, for example, the last one I will explain shortly. So the first two, they have different levels, level of the depth. So if I select one frame, I do prediction because my model have been trained already, so I could predict right now. For if you start from beginning, of course you have to train the model. Now we can see both model has predicted well in this region. Of course, we can compare very carefully and visually in the image. So you can compare the views. This is the ground truth, and this is the prediction. You can compare 2 different models, or you also have the scores. The scores is also based on the prediction, the difference between the prediction and the ground truth you have painted. And for this model, if I do this one, I could. I added this frame as the training data later because I want my model to predict everywhere in this image data correctly. You see the first the depth level 5 model, it didn't predict well here. This is the mistake. In my depth level 6 model, it predicted very well. So this is how I achieve the best model by comparing different networks and adding new training frames for retrain the model. And for the second one is trained after I have all the frames. So I did only one round for training, and it converged very quickly. The last one is from the pre-trained model. It doesn't show much difference. It's almost in theory, the pre-trained one will converge sooner, so it will take less number of epochs to get the good prediction. It's not that obvious on this demo case, but it produced almost the same result as the one I created from beginning. So after we train the model in the wizard, remember the wizard, the segmentation wizard is the tool to give you all the steps to finish all the steps and to train the model. And if the model has been well trained, you can publish that. When you exit the wizard, you have this dialog, so you can publish that. I already did that, so I don't need to publish again. After you exit the wizard and you have published the model to the main session, then you will be able to have that in this tool. We call it deep learning tool. It has all your deep learning models here. And this is the one I published from the wizard. And you can load it from here. You can either do you selected the image you are seeing now. You can do a preview. Preview is to apply this trained model to the current view, and you see all the pores has been labeled correctly. If you want double check, you see in this component the pore has not been labeled because the target is to label only the pores inside the solder balls. And besides the preview, you can also apply to the full dataset. By doing this, the program will apply the model to all this 240 images or image slices. And after that, it will give you a full segmentation of the volume. So this one is from applying the model. It will take 2 minutes. So I'm not doing that again. So if you see this is a result from the model segmentation. Is 240 slices fully segmented. So I'm going to show you very quickly. After the segmentation is done, we can do some analysis. For example, I can extract. This is one class from the multi-ROIs. Now I'm extracting two classes. One is the purple one is the solder balls, and the green one is the pores inside. So you see everything else is background. And what I want to do is I want to measure how many solder balls are here and what is porosity for each ball. And to do that, I
Let me
combine.
interrupt. You have 2 minutes. Can you? Yeah.
Okay, fine. So I just want to show it quickly, the quantification function in Dragonfly. So we can do the uname of this. Then this is the solid, this is the field solder balls. So we can say this is solderable field. Also, we have this green one, which is the pores. Then we can generate the multi-ROI from the ROI from what that means is from the this is the ROI. From the ROI, it means it label all the solder balls as one class. And by doing the multi-ROI, you see each ball has been labeled differently. So this is instance segmentation. So we could label each instance differently because they are disconnected from each other. So we can do this very quickly. Then it's the same for the ball, but for the pores, but the problem for the pores is some solder ball, for example, one ball may have two pores inside, and the two pores may not be connected. So if you do directly, you will separate these two as different instances, which is not correct. And I do this A and B, I do intersect as RY. So by doing this, by doing that, I have, you see the pores, this two has been labeled as the same class because they belongs to the same ball. So I would say this is pore per ball. Now I have two multi-RY. I could do what we called is the from the multi-RY, oh, not this one. From the multi-RY, I go to generator, the scalar generator. We have a cross index, then we choose the other, the pores per ball. Then we compute the cross indexing. This means I show it very quickly, and it shows here in this table. I can also compute the volume. So you see on this table, it shows we have 113 balls, and for each ball, for each solder ball, what is the volume of the total volume of the ball, and in that ball, does it have a pore inside? If it's 0, that means there's no pore inside. If it's 1, it means it's corresponding to the first, like here, corresponding to the first labeled pores. And by doing some Excel analysis, you will be able to get a list of 113 solder balls and what is the porosity for each one. And this is a quantification and a.
So, Dr. Kaur, sorry
Yep.
to interrupt you. Yeah.
Okay.
So actually, we are running out of time. I request
Okay.
you to please type your email ID in the chat box. So if any participants will have questions, they can ask directly. One question I have, that this software is available as a student version for free.
Well, this is complicated. We have different policies in different territories or countries. So I would say yes, we could provide the software for free for students, but
Okay.
it's not an official policy yet. We welcome students to try it and to work with us.
Okay. So you please type your email ID in the chat box. And thank you so much for this wonderful demonstration. I hope audience which want to perform the detailed microcity analysis, this demonstration will be helpful for them. So thank you once
Great.
again, Dr. Kao, for joining and for arranging time. I understand your busy schedule, and thank you so much.
My
So
pleasure.
yeah. So our next speaker is Dr. Ashish Agarwal. He's from RRCAT Indore, which is a body of the Department of Atomic Energy. So Dr. Ashish, can you please unmute yourself? So Dr. Ashish already joined. Just yeah. Hi. Can you please unmute yourself? Your voice is not coming. Hello.
Hello.
Yeah.
Yeah, speak. My voice is clear.
Yeah, now it is clear. So I'll just thank you so much for joining. I'll just quickly give your introduction, and then you can share your screen. So Dr. Ashish is working in neutron and synchrotron radiation physics section, technical physics division, BARC, Mumbai. He has been primarily working on various X-ray and neutron microimaging activities related to design, development, simulation, experimentation, data analysis, operation, and maintenance, and utilization for various applications. He has been involved in design, fabrication, and installation of imaging beamline, along with implementation of various advanced imaging techniques such as phase contrast imaging, tomography, real-time imaging, dual energy imaging, in situ imaging, and high resolution imaging. He has also initiated operation of imaging beamline, in which beam mode he has carried out synchrotron X-ray imaging based microstructure characterization and structure property correlation studies on several engineering and biomaterials such as scaffold, etc. Has also been involved in several collaborative research, not only for imaging experiments, but also for several non-imaging studies. With this, I would like to thank Dr. Ashish for joining. Over to you, sir.
Yeah, thank you for inviting me for this lecture. And
so I'll just stop recording because as you mentioned. Okay.